Well, thank you very much for inviting me here and giving me a chance to give a talk. I wrote my talk too far in advance, and then I made the mistake of looking at it. And I realized that I'm not getting my points across, so I figured I'll give you this version of the talk. So what do I want to say? C infinity rings are the right algebraic gadgets for working with singular spaces in differential geometry. So you could derive all the singularities away the way Rare explained to us, but if you don't want to do it and you want to look at the coarse moduli space, I suggest you use those things. And sometimes if you want to do classical mechanics, it's really hard to do classical mechanics on derived symplectic stacks. But you can do it in this setting. The other point is C infinity schemes are easy. Or at least they're easier than the ones you see in algebraic geometry. Trust me. And you can have vector fields. Right, for some reason, algebraic geometers never integrate their vector fields. And I guess if you know algebraic geometry, you know why they can't, you don't integrate vector fields in algebraic geometry, because they're transcendental. The integration would be transcendental. In this setting, you can. And differential forms. Croton calculus. So that's basically what I want to say in this talk. And so people who have to open their laptop and answer their emails can do it now. Right, so I want to go back not to 1990s, but to 1980s. So both Eckert and Rare talked about singular reduction. But I want to start by mentioning Richard Cushman. This is 1980s. And he observed that, so you've seen these. I'm going to use mu for the moment map. So if you have this moment map, ordinary equivariant moment map for an action of a Lie group, then you can define smooth functions in a reduced space, which you can think of as invariant functions restricted to the zero level set. And he observed whatever you need to assume to be happy with this definition. Proper actions will do. So he observed that C infinity M naught has a natural Poisson bracket.
This is sort of follow-up to the IL's question. You could also take the G invariant part of C infinity M mod the ideal is generated by the components of moment.
Yeah, it's.
That will in general be different.
Yes, you're going to get a different C infinity scheme.
Okay.
This one is going to be a reduced C infinity scheme. The other one doesn't have to be. That's probably the shortest way to answer your question. And this reminds me of something I also wanted to say. In the 90s, people talked about geometric reduction versus algebraic reduction, and there are different flavors, and people were trying to prove when one is the same as the other. They were basically working with all algebraic reductions are really geometric, except for instead of getting a space of functions in a space on a set, you were getting sheaves. And somehow that point wasn't observed at that time. Right? So we're thinking of these guys as smooth functions. On the reduced space, there is more structure. Right, so I say he observed it because he was not interested in theory. He wanted to compute examples. And so he was churning out computations. This was proved rigorously by Arms, Cushman, and Gatte around 89. There's more structure. So what's the structure? The structure is that this guy is a sheaf of C infinity rings on M naught, which is mu inverse of 0 mod G. Right, so I keep saying C infinity rings, but I haven't defined them, so maybe I should. Too long, didn't read. Right, this is how my kids talk. Okay, so what's the C infinity ring? So roughly, probably shouldn't do it here. The C infinity ring is a set A with operations. So you can think universal algebras if you ever run into universal algebras. Otherwise, just trust me. Of arities 0, 1, 2, and so on. And you get one operation, one area operation for any function, for any smooth function. And so zero arity operations are constants. So for every real number, you get an element of your C infinity ring, if you're thinking of them this way. And there are associativity conditions. So if you have a bunch of operations, you put them together, you compose with another operation that should be associative, right? And what a weird thing to do. And you also want that the projection maps, right? There are smooth functions on R. They should give you projections. So I'm using the lower index A for an operation corresponding to a function. I think that's a better notation than used in Joyce's book. So this guy is the projection. Ith projection. So what's an example? So in the case I started talking about here, of M naught, F sub A applied to a whole bunch of functions. On your reduced space is just F composed with functions, right? It's composition. And you can check that this thing is going to be, if these guys represent invariant functions, you take n of them, you compose with another with an arbitrary smooth function, you still get something invariant. And so you have these operations. And so this is a singular space, and you have the structure. I have two comments I want to make at the same time. So we'll do it here. So compare. So here is a weird definition of a commutative ring. A commutative ring R is a set R with operations P sub R. They go from R to the n to R for every polynomial with integral coefficients. Right? We're used to commutative rings as having like 2 or 3 operations, but you can have countably many. And we'll still give you, so what we're doing, right, what's the connection with algebraic geometry? You take this axiom and replace polynomials by smooth functions. So how else would you go from algebraic geometry to differential geometry? You replace polynomials by smooth functions. Right, and another remark, so if this guy happens to be a math, right, manifolds, the smooth functions on a manifold also have a structure of a C-infinity ring. And the definition is this. Here's the structure. Right, and for those of you who like operads, there are no operads here. Technically, right, if, so whenever you have operations in associativity conditions, some people start thinking operads, but this is a Leverrier theory. Leverrier theory. And my friendly homotopy theorists tell me there is a big difference in homotopy theory between the two. Right. So C-infinity rings form a category. Or if you don't like this language, if you have 2 C-infinity rings, there is a notion of a homomorphism. A map of C-infinity rings is a map of sets with a preserved structure. We preserve the operations. So you might notice that if you have 2 manifolds and you have a smooth map between them, the pullback map is going to be a map of C-infinity rings because it's going to preserve the operations which are just defined by composition. So you can shove manifolds into C-infinity rings. Oh, here is an amusing fact. C-infinity Rn is a free C-infinity ring on n generators. So if your manifolds are second countable in Hausdorff, they are finitely generated as C-infinity rings, and in fact, they're finitely presented. They're very nice C-infinity rings. The unusual thing is that if you look at manifolds with boundary, they're still finitely generated as C-infinity rings, but they're not finitely presented. So you could give up on finitely presented. On what? Could I give a hint? I can give it, right? Why is this a free C infinity ring? Because it's, I don't, sorry?
For manifold, I guess you're embedding it.
Yeah, you can embed manifold with boundary RN, but then you start looking at the ideals of functions that vanish on the manifold with boundary, and it's not finitely generated. Right? Look at the interval 0, 1 in R. Look at the functions that vanish on the interval 0, 1. And if you look at the ideal of functions that smooth functions that vanish on 0, 1, this ideal is not finitely generated. But don't ask me to prove this. Right, so if your interval is not finitely presented, you don't want to go this way. What else? There's also a notion of a local C infinity ring. In fact, there are several, but one of them turns out to be the one you want. Or there's a consensus that only one of them kind of makes sense. And once you have this, hence local C infinity ringed spaces, full injuries, I'm just going to call them this. This is a bit of a jump, right? If you have, so what's a local C infinity ring space is going to be a space with a sheaf of C infinity rings, like a manifold. And the stocks have to be local C infinity rings. And germs of functions on a manifold, they're a local C infinity ring. They're a local ring. Right? And then, so C infinity schemes make sense. And while I'm at it, this is the book, 1980. So I told you I'm going to keep going back to the 80s.
Roughly the difference between a local C-infinity ring space and C-infinity schemes, that you have some preferred local model that you...
Okay, so let me just say what I want. Let me say something else and hopefully I'll answer your question.
Let me complement that question. Is this an adjective or a noun?
Which one?
The local, is this a property of the C-infinity ring or is it additional?
It's a property. Right, there is a unique maximal ideal of a certain type. You want the quotient to be the reals, as opposed to some arbitrary field. Right, so there is a functor. What the book actually did, he constructed a functor spec from C infinity ring, contrary ring functor to local C infinity ring spaces. So that gives you the essential image of the functor are the affine schemes. You can glue them together. You can define projective schemes. But the funny thing is that if you look at the projective space, RPN, that's an affine C infinity scheme. So it's not clear why you would want projective C infinity schemes, but there are papers about them. Oh, and another thing I probably should say, this is not like spec in algebraic geometry, because it can take a non-zero C infinity ring and send it to an empty space. It's not at all, the intuition you might have from algebraic geometry is not going to serve you as well as you hope. Right. Local C infinity ring spaces. Yes. The funny ring is you could have is take C infinity Rn, mod out by the ideal of compactly supported functions. Take spec. You'll get nothing. So spec is the empty space with the zero sheaf. Yeah, the local is that you have R points, and that's the only thing you look at. And there are various reasons why you want to look only at R points, because if you have a manifold and you want to get the points back from smooth functions, you should just look at R points. And so the definition of a local C infinity ring is rigged so that the unique maximal ideal is the unique R point. Spaces showed up in the 70s in the guise of differential spaces. In the sense, there are lots of things in differential geometry called differential spaces. Sikorsky. The underlying topological space. So what's a local C infinity ring space? It's topological space with a sheaf of C infinity rings, and the stocks are local rings. And you need local rings so you can talk about morphisms.
You said that this is not your ordinary garden variety spec.
This is a completely different spec.
Sometimes, in algebraic geometry, sometimes you think about prime spec and max spec.
Right, so not prime spec, not max, not even max spec, just R points, right? And the thing I didn't say here because, well, I don't know why I didn't say that. How would you define spec in general, right? Not as a construction. It's the right adjoint to the global sections functor. So if you define local C infinity rings the way I did, it's a theorem that it has a right adjoint, and it's spec. So what the book proved is the existence of this right adjoint. And it doesn't matter how you construct it. But there is a construction, and you can write things down in gory details. And if you start with smooth functions in a manifold, as long as it's Hausdorff, spec will spit out the manifold.
So for differential spaces in the
Right.
sense of Sikorsky, one big thing is that the topology is coming from the smooth functions that's equivalent to having smooth thumb functions. Is there anything of that sort that?
If your local C infinity ring space is nice enough, there are partitions of unity. But you have to have restrictions on the topology. Right. And there are theorems in Joyce's book on algebraic geometry. So the title of my talk is sort of a reference to Joyce's book on algebraic geometry over C infinity rings, right? So this is the way I got into this, I was talking to some engineers, and they needed to do things on singular spaces. And I told them, well, Joyce wrote this book, and it probably has everything you need. And then I went and looked at the book, and it didn't, because it didn't have vector fields, and it didn't have flows. And this is when I got hold of Yael and said, Yael, we have to get to work. So I'm trying to get to this. Right. So here's a definition. And the point I want to make, it's a technical point, so I apologize. Differential spaces are local C infinity ring spaces. They're not necessarily schemes, for the reasons that might become clear. So a differential space, I'm going to write down a concise definition, is a pair F. M a set F, a set of R-valued functions on M. So you could think of them as smooth functions that show up in the singular reduced spaces that Cushman worked with. Subjected to conditions. So one, for any h, for any n, basically you want this guy to be a C infinity ring, F. So for any n, for any h1, f1 through fn, and f, for any h, C infinity Rn, H composed with f1 through fn is back in F. So this just says that F is a C infinity ring with the operations defined this way. And two, give M the smallest topology such that functions in F are continuous. And I don't know how well I'm doing with time. I'm going to take a shortcut. Sorry? Okay. So here's my shortcut. So now you have a topological space. And if you have a topological space, you should probably have sheaves. Not everybody believes that, but. So smooth functions should form a sheaf. F's are smooth functions. Elements of F are smooth functions. So you want to say you have a sheaf. How do you say you have a sheaf? And how do you get a sheaf of smooth functions on a manifold from globally defined functions? You restrict it to open sets. In general, once you've restricted smooth functions to open sets, you get a sheaf. Here, you don't know, right? So consider the pre-sheaf. P on an open set, which take the smooth functions and restrict. And now the sheafification SHP is a sheaf by definition, and we require, this is not how it's going to be written in any books on differential spaces, but it's the same, that you get global. Once you sheafify, you get global sections back, right? This is like our commutative ring, X, OX is spec, then global sections of OX is back to where you started. Sorry, did I write too low? I'll move it. Right, so this is the kind of thing you do. Right, that's a differential space. And but there is no reason for the R points of the differential space to correspond to points of the set you started out with. And this is, this definition makes differential spaces easy to work with, and it drives me crazy. Because if you want to try to do things you would want to do with schemes, you can't. So for example, if I take the reduced space, and I can take F to be smooth functions in the reduced space, is a differential space. Right? What's the corresponding sheaf? You just can restrict to open subsets. You don't have to sheafify anything.
Well, not every such an open subset comes from the extended.
All right, sorry, you do have to sheafify. I stand corrected. This is why you want to sheafify. Or you can define, the structure sheaf on the set U to be, I don't know if I'm going to screw it up. Something like that. So I didn't tell you what utility is, but you take an open set. Yeah. Right, you could. Sorry? None. Proper action, if you want to. Right, so differential spaces form a category. And if you don't want to deal with sheaves, you don't have to. So a map from one differential space to another is a continuous map. I don't know, F from M to N, such that for any element of Fn, H decomposed with F is back. Right, pullbacks of smooth functions are smooth. Well, I want to define, I can put extra conditions if I want to. You could probably fiddle with it and get away with less, but I don't want to. So the point is, so you think of these things as being smooth maps. For manifolds, they're exactly smooth maps. You can actually prove that differential spaces actually embed in local C-infinity ring spaces. And it's a bit of a miracle that's been known for a while. So if you know locally ring spaces, you know that you need to have a map on spaces and a map on sheaves. In this case, you don't need to have a separate map of sheaves. It's determined. And apparently it's been known for a while because I found it in Varadarajan's book on supergeometry.
So are these, so again, are these examples of locally C-infinity spaces?
Yeah, any differential space is an example of any differential space is an example of local C-infinity ring space.
Local C-infinity ring spaces is something more general?
Yes. So going back to the discussion about algebraic reduction, you do algebraic reduction, you actually get a C-infinity ring, take spec, you get a sheaf of things on the underlying set of R points. And that sheaf of things is not necessarily a sheaf of functions.
Okay. So, yeah.
Right? So in particular, curves from some interval to a differential space makes sense. So here I is an interval, not necessarily open. And there is a reason why I don't want this interval to be necessarily open. And it has to do with an annoying issue in differential geometry. so I'll get it off my chest. If you have a closed disk, and you take the vector field ddx, so this is x squared plus y squared less than or equal to 1, what's the flow? If you're a physicist, you know exactly what to do. If you're not a physicist, you're stuck thinking about, well, here's my disk, here's R, and the flow domain should be, I should intersect it with a cylinder, a slanted cylinder like this, right? And now my abilities to draw things kind of fail me, right? You're going to get an intersection of two slanted cylinders, and you'll discover there is a singularity right around here where you have 4 edges coming in. So it's not a manifold with corners, but it's a perfectly nice differential space because it's just a closed subset in R3. I haven't taught calculus for a while, so vector calculus, so I forgot how to draw this picture. But the intersection of two cylinders is always in calculus, right? So this is so the thing I'm about to mention solves this problem and a few others, right? But then I should probably define vector fields in differential spaces. So what's a vector field? You go through your pile of definitions of vector fields and manifolds. Tangent bundles, probably not going to work. Actually it does, but they're not going to be vector bundles. So a vector field on a differential space F is a derivation V from F to F. One thing I forgot to mention, any C infinity ring is an R algebra, because you can forget most of the operations except for the ones you need for the R algebra. And you could define derivations, this thing to be a derivation of R algebras. It's not quite the right definition, but in this case it makes no difference. Thanks to somebody's theorem, Yamashita. Right. An integral curve of V is a map, is a curve gamma from I to M such that, and you write your favorite definition of an integral curve that doesn't use coordinates. So this is a T. So that kind of makes sense. So in this example, the integral curves are going to be things like this. And they will go from a closed interval to a disk. And they're going to be smooth maps. These are maximal integral curves, right? So there is a theorem, which I forgot to mention last time I talked here. This is about 2003, so we left 1980s reluctantly. Derivation on a differential space which is locally isomorphic to a subset of Rn. One thing I didn't emphasize so far is differential spaces don't need to be anything finite dimensional. You take a Banach space, you look at smooth functions on the Banach space, they'll form a C infinity ring. I'm sure you can get a differential space out of that. right? If you try to integrate vector fields on infinite dimensional spaces, I guess you have to have some conditions for the Picard theorem to work. It doesn't always work. But so we're going to solve this problem by defining it away. As maximal integral curves. So that, but the thing that bugged me was that there were no flows. Wait, this is just says if you pick a point, you can find an integral curve passing through the point at time 0. But what about smooth condition? Smooth dependence on initial conditions. You better have that, right? So, yeah. Oh, as a differential space. Yes. Yeah, I start with my differential space, take a point, has an open neighborhood, and I want every point to have an open neighborhood that looks like a subset of Rn. And I, as differential spaces. No, differential spaces. And I haven't told you how to give differential space structure to a subset of Rn because, right, so because I want to. 23? No, I think it's officially 23. Right, one thing I should have said here, there is a Whitney embedding theorem for such spaces. Under reasonable conditions.
Which I do not understand.
But there are like 4 published proofs.
Oh, I guess I understand.
Okay, so the way I want to formulate the theorem, MF differential space locally embeddable.
So, Eugene,
Yeah.
you want to
Nope.
someone else can go take
I'm not doing anything.
some.
I'm not going into technicalities because I'm not allowed to talk for another 2 hours, right? Right. Then Hausdorff. Right, if it's embeddable in Rn, it has to be Hausdorff. And second countable. Then derivations have flows. So you have a differential subspace of your manifold of your differential space cross R, and you have a flow that would define the way you would by putting together all of the integral curves, maximal integral curves, and it's smooth. So smooth dependence on initial conditions.
Such a differential space which is locally isomorphic to Rn, which is not more than an manifold balance.
Oh, you know, you could take x, y equals 0, normal crossing. It's not a manifold with boundary. This is a very nice differential space because it's finally presented. Right. How many minutes? 5. Okay. I think I'm in Ray's situation. 1. So C infinity rings. So this, again, back to 1980. And back to the book.
So,
Yep.
so if you take any subset of Rn and you just reduce to the function to be
Could we do that after the talk? So for example, they hid this theorem from everyone. I wish, when I was in grad school, I knew about it. If my ring is smooth functions in Rn, the Caylor differentials in this sense are theorem forms. If you try to do it with commutative algebra Caylor differentials, you'll be screwed. You'll get something that's not, you get a module, but it's not even countably generated. There are papers written on how many generators this module would have to have. This one just gives you differential forms on the nose. And then in 2 minutes or less, what can you get? Sorry?
3 if it helps.
Okay. So if I have a C infinity ring, I don't know what to call them, so I call them C infinity algebraic theorem forms, which is a pun on Grothendieck's algebraic theorem forms. For C infinity ring A. Okay, so you get A, Caylor differentials, and then you have to extend it to higher powers. And the issue is this module is not nice. So there are relations between generators, and you have to do a bit of work to get, I shouldn't work here. Oops, this is the wrong thing. But fortunately, the stack project tells you what to do in the commutative algebra sense, and you can adapt it. So you just rip off the stack project. Well, once you have this, you get differential forms on, so for a local C infinity ring space, you get a sheaf of differential forms. This is a very quick way of saying it. I always run out of time when I want to talk about Cartan calculus. Well, for a C infinity ring, and this is actually
Another L and another U, otherwise. Yes. No. 3 lines down. Calculus.
oh.
He's running out of time.
Well, you have contractions. That's basically, if you have a derivation, that's the universal property of Caylor differentials. They extend to a derivation of this exterior power at degree 1, degree -1 derivation of this graded commutative algebra. and then you cheat. The problem is that for general local C-infinity ring spaces, it's not clear how to define flows. And for C-infinity ring, it's not clear how to define flows. So you can define Lie derivatives as the commutator. And in fact, you can come up with examples of differential spaces. My favorite is the Cantor set. DDX is a vector field on the Cantor set in this sense. Its flow exists only for time 0. Good luck trying to get Lie derivatives out of flows. It has you can define Lie derivatives, and this way, that works. And once you have this, you can move to sheaves, local C-infinity ring spaces, and you get Cartan calculus. The issue, so you end up doing is graded differential geometry, like the one Ray talked about, but unlike the graded commutative sheaves that Ray talked about, or not talked about, right? They're locally free sheaves or freely generated commutative algebras. Nothing is locally free here. And 0 minutes? Right, so.
We can say 1 minute.
Okay, so let's take A to CB, C infinity of R2 mod xy equals 0, or mod xy, I guess. You could ask what this is going to be, and you would expect it to be 0, but it actually has, right, this is something I learned from Jordan. If you sheafify this guy, you get a skyscraper sheaf. You get something non-zero at the origin and 0 everywhere else. So I'll finish with that. So these things are kind of weird. But you know, when I
actually do recover.
you get a singular, right? This is singularity. Something weird should happen. This does. You get a skyscraper sheaf.